let's get started. Today is the last lecture by Hiroshi.
Okay, thank you. So I just realized that I went through just about half of my lecture note. So we'll select some material from the rest of the lecture note. And one thing I want to remind you is that in the last lecture, I argued that this eternal black hole in anti-Rita space is dual to thermal field double state in the tensor product of conformal field theory Hilbert space. This was proposed by Marder in 2001. And, but then I would also like you to remember the causal wedge reconstruction or ADS Lindlar wedge reconstruction that we discussed earlier yesterday, which is to say that if you have just one boundary, and then if you have a causal domain on the boundary of some region A, so you have this causal domain A in CFT. So suppose A is some part of the space-like section of conformal field theory. You can draw causal domain, the domain of dependence, please excuse me, associated to this A and denote it D of A. So this is on the boundary of ADS. And suppose this is that causal domain. So now I make this into one dimension. So, and then there is a causal future and the past. So this is a union of, intersection of future and the past of this causal domain. And what I was discussing based on HKLL construction is that if you use Hilbert space on this segment of conformal field theory, you can reconstruct everything inside of it as far as local operator is concerned. If you apply this philosophy here, what this is telling you is that if you utilize conformal field theory on this side, you can reconstruct everything on this wedge outside of the black hole. On the other hand, if you use the conformal field theory on this side, you can reconstruct information on this side. So this suggests the following, that this side does not know over here. So if you trace out over here for this thermal field double state, then you have a density matrix, finite temperature density matrix for, so this is a thermal density matrix for the conformal field theory 1. So this reconstruction suggests that this knows about this region 1. On the other hand, if you trace out the other Hilbert space of the other conformal field theory, this side, then you'd be reconstructing this. Beg your pardon? I denote this to be 1 and this will be 2. The matter of notation. Okay? Okay, so this will be a reconstruction. And this picture fits very well on what's happening on this side and what's happening on this side. Because on this side, you just have a tensor product of conformal field theory. There is no direct interaction between them. You're just selecting the entangled state. This is reflected on the fact that there is no communication between this region and this region. That these are space-like separated, so there are no communications between them. Nevertheless, they are entangled. Since there is no communication between them, so that means that whatever you do on this side cannot influence events on this side, and vice versa. So that is related to the fact that there are no interaction between these conformal field theory. So whatever you do in this conformal field theory cannot influence this. However, if you make a measurement, observation of this state, the outcome of the observation can influence the outcome of observation in the other conformal field theory. And this is reflected on the fact that you can jump into the black hole from this side, and you can jump into the black hole on this side, and you can meet over here. So the fact that in addition to these regions associated to these conformal field theory, specifically for left side and right side, you have 2 additional regions where you can meet. Is related to the fact that these states, even though there are no direct interaction between them, are nevertheless entangled. Okay? So now, in fact, let's discuss the nature of entanglement. So if you compute, let's compute the entanglement entropy, starting with partial trace over Hilbert space for the second conformal field theory. So sum field double, tensor sum field double. Okay, so this is, so then of course by definition you get back to this. So our entanglement density matrix is this. So therefore, if you compute the entanglement entropy for the region 1 for this sum field double state, then this is trace over Hilbert space 1 of rho I log of rho I. And so if you calculate it, you can compute it and then find that this is actually expectation value of Hamiltonian for at this finite temperature minus the log of the partition function, finite temperature partition function. But this is nothing but the entropy, thermal entropy of this canonical ensemble. And it's given by the Bekenstein-Hawking formula, which is 4G times 2 pi d over 2 gamma d over 2 times r d minus 1, where r is the radius of the horizon of the black hole. And this is basically the area of the horizon. For the black hole in d plus 1 dimension. For d plus 1 dimensional space-time, the black hole horizon is d minus 1 dimension. And if the black hole has a horizon has a radius r, then this is the area divided by 4 times g Newton is reproduced in the large n limit. Gamma function. Because well, this is the volume of the unit sphere in d minus 1 dimensions, right? Now this has also the following interpretation. As I pointed out yesterday, between region 1 and region 2, even though they are not causally related, but they are geometrically connected. Namely, that if you take space-like section like that, where they are connected, and the geometry looks like this. So this is the geometry of this space-like section. So I'm suppressing the time direction. This is a space-like section where you have SD minus 1 on this side and then goes here. And then this asymptote to hyperbolic space on both sides. This goes to CFT2. This goes to CFT1. And then this geometry is called the Einstein-Rosen bridge. Okay? So the radius, so there is this actually have this this picture. I draw this picture in such a way that you can see that there is actually minimum area region over here, and the radius r is this radius r, which is related to the inverse temperature beta by this relation. This is a space-time dimension for the conformal field theory. Like that, okay? So that means that this also have an interpretation. The entanglement entropy for the conformal field theory 1 has also an interpretation that it is 4G Newton is dividing the area of the minimum surface separating CFT1 and CFT2. You can interpret the same thing in this way. So namely that these two conformal field theories are spatially separated. And then this is drawn here like a point because I projected it in 2 dimensions. But this is actually d minus 1 dimensional sphere. And the area of this sphere is actually related to the entanglement entropy between them. Okay? So now these are the very interesting features, namely that the area of this black hole, area of this Einstein-Rosen bridge is exactly proportional to the entanglement. You can also see that from here too, because as area grows, as the area becomes small, beta becomes small. So that means that, as area becomes small, there is something wrong with this picture. Is this T? I must have made a mistake. Because as temperature grows, the beta should grow, the R should grow, I believe. So sorry? Temperature, yeah, so this is consistent. Yeah, okay, good. So D times R squared. Yeah. So excuse me. Yeah, anyway, so as R grows, the entanglement grows. And as R becomes small, the entanglement becomes small. So this is related to the fact that, as I said, even though these two conformal field theories cannot influence each other directly because there are no direct interaction between them, but nevertheless, they are connected by entanglement, which is reflected on the fact that they are connected in this case by the size of the space-like section separating them. Okay? So this observation is very interesting that somehow, it is interesting for two reasons. One is that the entanglement itself is influencing the geometry. That somehow as the entanglement grows, the size of the bridge grows. And so therefore, geometry connecting the two conformal field theories is growing. So somehow entanglement is building up the geometry in the bulk. And the other interesting feature is that this entanglement entropy is related to the area separating the two things. So this motivated Shinsei Ryu and Tadashi Takayanagi to propose more general formula for entanglement of a given state. So let me first remind you general causal wedge reconstruction or ADS Lindlar reconstruction that I already reminded you over here, but let me just state it in the following way. So I told you that if you have some region A, and then you have a domain of dependence A, then you can reconstruct the intersection of the past and future of this domain. So, but I should also mention that, suppose you have a pure state. Suppose you have one of these pure states. This certainly is a pure state in this direct product. This is a pure state in the direct product conformal field theory. So similarly, suppose you have just single ADS space, and then suppose you have some pure state. In this case, if you have some region A, then you have this causal domain associated to A. And then you have a complement A bar, and then there is a causal past and future, intersection of causal past and future associated with it. So this is this region. So if I draw it this side on this side, then you have a causal domain of dependence for D of A bar, and then they cover this side. So for the space-like section, say T equals 0, suppose this is the picture T equals 0, then the entire bulk geometry, this is any pure state in the code subspace, which is describable by smooth geometry. Doesn't have to be ADS, some smooth geometric solution for the gravitational theory. Then this is again divided into two regions. So even though this is a single geometry, but naturally divided into two domains, separated by the fact that you have this causal patch on this side and you have causally related region on the other side. So this suggests, well, if you compare these two pictures, this suggests that just like the size of the Einstein-Rosen bridge, connecting the two causally disconnected but entangled region, gives you the entanglement entropy, it is natural to expect that the area of this gives you the entanglement. So this led Ryu and Takayanagi to propose that for this kind of pure state, the entanglement entropy is given by the area of this surface, let me call sigma, associated to A. And this has various features. The sigma of A should end on the boundary, should be anchored by the boundary of A, and it should extrematize with respect to the metric in the bulk. And this has been checked in various examples. This proposal has been checked. For example, I mentioned in CFT2, we have this formula by Cardi and Calabrese and Cardi that I mentioned the other day, where if you have, so it's 1 plus 1 dimensional conformal field series. So if you consider boundary with length L, then the entanglement entropy is given by this plus constant. So this is what I mentioned the other day. And you can show that if you consider a pure ADS, so this is for the vacuum state. So if you consider pure ADS3, and then if you consider a minimum surface ending for the region with length L, then and they evaluate the area and divide by 4G Newton and translate that into conformal field theory language. This is exactly reproduced. This is a hyperbolic space, so the metric actually diverges near the boundary, so you have to introduce some regularization, which is related to the fact that on this side you also have to introduce ultraviolet regularization, which affects this constant piece. So this ambiguity also matches up in that sense. Okay? So, but this leads us to new kind of idea called entanglement wedge. Which is a slightly different notion compared to the causal wedge that we have been talking about. So I have defined in a couple of lectures ago the notion of causal wedge, which is that if you take the region A, so I draw it over here, if you take the space-like subspace of the space-like section of conformal field theory, you can define domain of dependence. And then you can consider past and future of that domain of dependence, consider intersection. Then you have a causal wedge associated to region A. You can also define entanglement wedge associated to this region, which is naturally related to the Ryu-Takayanagi surface. In some cases, causal wedge and entanglement wedge are closely related, but in other cases, they are not necessarily related. And in fact, generally speaking, entanglement wedge is bigger than causal wedge. So I have to first define what entanglement wedge means. The entanglement wedge is the following notion. So you have, suppose you have a state which asymptote to the anti-Rita space towards the boundary. So you have some solution to gravitational equation satisfying the ADS boundary condition. And consider some space-like section of this. And then, again, as usual, I consider some section, some space-like section A, for example. So then you can consider a Ryu-Takayanagi surface associated to it, which I denoted by sigma of A. So then you have some region surrounded by A and the Ryu-Takayanagi surface. So let me denote this by this character small a. And then entanglement wedge is defined as a domain of dependence, not of big A, but small a. So entanglement domain is entanglement wedge is a region where in the bulk. So let me So I cannot draw it here, so let me draw it in this diagram. So suppose this is small a. So I suppress this dimension along the boundary. So suppose this is small a, then what you do is just like before, you consider the past and the future of this a, and then consider intersection of this. So this is the entanglement wedge. No, I didn't speak it correctly. So what I meant by the causal, the domain of dependence is that you pick a point A, so this region is defined in such a way that if you pick any point inside of this and then extend this point along any time-like path, it would have to necessarily intersect this small a. So that's the definition of the domain of dependence. So for example, if you pick a point here, you can extend this indefinitely in past and future in time-like direction without intersecting small a. So you see that this point is outside of this domain of dependence, whereas this point is inside of this domain of dependence. So this is the definition. So this is the entanglement wedge. And you can actually show that entanglement wedge in general is bigger than the causal wedge. So for example, so this can be most easily be seen when you consider the case where the boundary region A has multiple components. You can certainly consider a case when the A has a multiple component. All these definition does not prevent you from doing that. So suppose you consider a case when you have the region A has multiple components. So suppose the region A is a union of these fellows. Okay? So, and then here I'm just considering the space-like section of these wedges. Okay? So if you have the situation like that, the Ryu-Takayanagi surface would go like that. The definition of Ryu-Takayanagi surface is that it's a minimum surface connecting the boundary of the region. But here you have two regions, so you have four boundaries. So, well, in this particular case, when the boundary is one-dimensional, but you can, in more general case, you have two boundaries. These are connected. But suppose A is slightly bigger. So suppose A is slightly bigger, and suppose A goes like this, and then goes like this. So this is one segment of A, and this is the other segment of A. Okay? So in this case, if you are interested in Ryu-Takayanagi surface, you'll be choosing this type of boundary. So then from this definition of causal wedge, entanglement wedge would choose this. Whereas for the same configuration, the causal wedge will be smaller because causal wedge will have to actually, if you follow the definition of causal wedge, it will have to choose the other region like that. And this is the causal wedge. So if I draw it over here, it's going to overlap this region. But then these regions in the middle are not causally connected to either of these. So if you consider domain of dependence of A here and A here, and if you pick a point here, this point is spatially separated from these points. So you cannot send a signal from here to the causal domain of dependence of A here. So this point is not included in the causal wedge. Causal wedge would be like that. On the other hand, this should be properly regarded as entanglement wedge from this definition. Okay. Yes? So they overlap. Yes, well, this is included in here. Yeah, well, if this is bigger, then they could overlap. But for example, you can actually come up with a situation where they don't touch with each other. Oh yeah. So there is one more condition I should have mentioned, which is that the surface has to be homologous to A. So this is the case when, so in pure state, often you don't have to worry about it. But when you have a black hole, for example, then you have a horizon. So this is, so I should mention that in Ryu-Takayanagi formula, there is a condition. If I have time. So I have about 40 minutes left, I guess. So in Ryu-Takayanagi formula, we have a condition called the homology constraint. That is that the Ryu-Takayanagi surface has to be homologous to the boundary domain A. So suppose you have a black hole and you have horizon. So if A is small, well, you can choose like this. So then this would be homologous to A. But suppose A becomes bigger, and then suppose A covers this region. Then you can have two types of minimum surfaces. You can have a minimum surface which goes like that, or you can have minimum surface which actually goes like this. So you have these two possibilities. So it turns out that the homology constraint requires this condition. And in fact, this gives you the correct result, because what you can see is that as this becomes bigger and bigger, eventually what minimum surface chooses is that this would grow. So then this is going to pinch off, and then it's going to become like that. So this will be the so this combination of this cycle and this cycle is still homologous to this boundary A. And eventually this disappears. So that means that when A covers the entire boundary A, then the Ryu-Takayanagi surface in this case will be the horizon itself. And that's the correct answer, because the entanglement entropy for the entire region is the Bekenstein-Hawking entropy, as we calculated over here. And so this gives rise to the correct answer. And in fact, you can also see that from this type of picture, that when A is small, then it goes like that. But then when A grows, you start growing toward the boundary. And then as A wraps the entire space, you need to seek out the minimum surface, which is homologous to this. And minimum surface homologous to the boundary is this neck of the Einstein-Rosen bridge. So this fits with this kind of picture here. Okay? So, but the fact that, so this existence of this entanglement wedge suggests that the reconstruction idea can also be possibly generalized to the domain bigger than the causal domain. You can ask, well, can you actually reconstruct states in entanglement wedge rather than the causal wedge? So in the remaining half an hour, I would like to actually give an argument that you can actually reconstruct local operator in principle in this larger space of entanglement wedge rather than the causal wedge. But in order to do that, I have to tell you a little bit about the various entropy inequalities that you can derive for entanglement entropy. And fortunately, I know that last week, Nima Al-Kani Hamed discussed entropy inequality, in particular, the strong subadditivity. And he, as I watched his video, he was deriving that from the positivity and the monotonicity of relative entropy. Do you remember that? Excellent. So I don't have to go through the derivation of this, and but I will be utilizing that. Okay, so entropy inequalities. So I think that Nima was talking about the strong subadditivity. And if you remember my first lecture, then strong subadditivity was closely related, is related to the property of mutual information. So this is a mutual information. So mutual information is a information quantity that tells you that how much you learn about A when you learn about B, right? Or no, more precisely, how much uncertainty about A is reduced by learning about B. So that's a mutual information. And gaining information should also always give you non-negative amount of information for the other quantity. So that means that this has to be positive or non-negative. And that is actually called subadditivity. And the other condition is that if you learn something more, then you'll be less uncertain. That would be the sort of slogan. And so this can be summarized in this type of formula. And then this is actually strong subadditivity. And then almost just a year after Ryu and Takayanagi proposed that formula, it was pointed out by Matt Hendrick and Takayanagi that Ryu-Takayanagi formula actually satisfies this strong subadditivity. So that was sort of a very nice confirmation of consistency of the Ryu-Takayanagi proposal. And as Nima was showing, that deriving this in general quantum system is very hard. But deriving this for a Ryu-Takayanagi surface is actually relatively simple. So let me just explain that in one line. So suppose you have region A, B, C, and suppose these are entanglement entropy for A, B, C, etc. So then Ryu and Takayanagi says, so what strong subadditivity says? Strong subadditivity says that SAB plus SBC is greater than or equal to SB plus SABC. Okay, so let me draw these four terms pictorially here. So SAB would be Ryu-Takayanagi surface like this. So namely the area of this surface divided by 4 Newton. SBC would be this. So this would be the right-hand side. In contrast, the left-hand side, excuse me. In contrast, the right-hand side here is SB, which is this, and SAB, which is this. Do you see that sum of red curves is less than, so sum of the lengths of the red curve in reds is smaller than the sum of the white curves? And can you see why? Well, it is easy to see because this red curve here connecting a boundary of B is homologous to the one here. So evidently, this is longer than this because of the triangle inequality, or the fact that this is actually stuck at the intersection here, so this gives you additional constraint. So this is actually the minimum surface. And this is a surface with one additional constraint, so this should be, in general, bigger. So reducing this over here should reduce the area. Similarly, moving this up over here should reduce the area. So that means that sum of these should be less than this one. So this is a very simple derivation of strong subadditivity, which was actually more generally difficult to derive in the general circumstance. So the Ryu-Takayanagi formula is supposed to be applicable for, actually I should have mentioned it. So this formula was originally proposed for a static state, or more generally a state which is time symmetric under reflection along the space-like surface. And then subsequently, Fubine, Rangamani, and Takayanagi proposed more general formula for time-dependent case, and those are called HRT formula. So you can ask, well, is strong subadditivity true for HRT formula? And so for Ryu-Takayanagi formula, therefore, for Ryu-Takayanagi formula, strong subadditivity can be proven in this way, right? But for more general HRT formula, actually, the same kind of argument works, provided that the space-time satisfies some null curvature condition, which is to say that for any k, which is null, that means that k squared is 0. This has to be non-negative. So if you think that the geometry satisfies the Einstein equation with cosmological constant with matter-energy momentum tensor, then the matter-energy momentum tensor should satisfy the null positivity condition. Null energy condition, excuse me. So if that is satisfied, then you can actually derive strong subadditivity condition. This was shown by Alan Wall. 1, 2, 1, 1, 3, 4, 9, 4. So this is entropy. This is a strong subadditivity condition. And you can ask, are there any other inequality you can derive for Ryu-Takayanagi formula? And in fact, understanding entropy inequality in general is a very interesting question. It is known that for general Shannon entropy, that is a classical entropy that I talked at the very beginning of my first lecture, it has been proven that there are infinitely many independent entropy inequality for a general number of regions. And it was actually very recently proven, just 10 years ago. So even though this is about statement about classical Shannon entropy, but it was just proven 2007 by Matas that there are infinitely many entropy inequality for Shannon entropy. For Neumann entropy, for general quantum system, it's not known, although there are numerical evidences suggesting that these are also infinite. Now, recently, Nimbao, Sefer Nezami, Bogdan Stoica, and James Sully, and Michael Walter, and myself proved that for Ryu-Takayanagi surface, actually entropy inequalities are finite. The independent entropy inequalities are finite, and can be classified by finite algorithm for every given number of domains. And we were able to actually classify entropy inequality for small number of regions explicitly, and enumerate them. So I actually was planning to talk a little bit about that, but in view of time, I will skip this subject. But I just wanted to mention that the totality of entropy inequality satisfied by Ryu-Takayanagi formula is in principle knowable, and there is a finite algorithm to classify them. And in fact, there are inequality generalizing this type of strong subadditivity inequality for more number of regions. And those have various interesting interpretation and are characterizing entanglement property of kind of state which belongs to the Causal subspace. That is the kind of state which can be described by geometry, smooth geometry in the bulk. But given the time, I would like to move on to another entropy inequality, which, as pointed out by Nima, is closely related to strong subadditivity, which is an inequality involving relative entropy. So this is actually a very important notion in information theory, and its significance has been sort of motivated in Nima's lecture, so I don't have to go through that. But let me just remind you that relative entropy is defined for given two density matrices. Relative entropy is a quantity which somehow tells you how close these two are. So it's like a distance, except that it's not quite symmetric in rho and sigma. So relative entropy is defined as trace of rho log rho minus trace of rho log sigma. So this is the relative entropy. And it has various important properties. I think that one of the fundamental property is that this is actually non-negative and is equal to 0 if and only if rho is equal to sigma. So this is actually a very important fact, that if relative entropy vanishes, then that means that the two density matrices has to be identical. I'm going to use that, so please remember this. And another useful thing is that for quantum field theory, the entanglement entropy requires UV regularization, whereas in this combination, they are canceled. So it's actually a UV finite quantity. So it's more mathematically well-defined. And it has various inequalities. This is one of the inequalities. Another inequality is that if the region A contains region B, then the relative entropy between the entanglement density matrices associated to rho A and rho B also increases. So this is known as monotonicity of relative entropy. Okay, now we can calculate this kind of relative entropy for holographic cases. And for example, you can consider the following object. So suppose let's say sigma is a ground state. And then rho is some excited state. But still in the code subspace in the way that I defined. So the nice thing about ground state is that if I choose A to be ball-like region, so you have a D minus one dimensional boundary, which is a sphere. And then on the sphere, you can have a D minus one dimensional ball. So if I choose A as a ball-like region, then I can actually find an explicit expression for log of sigma A. So minus of log of sigma A is called modular Hamiltonian. And in particular, when A is like ball-like, which is whose boundary is a D minus two-dimensional sphere, then explicit form of HA is known. It's actually one of the conformal generator of the boundary. And the way you construct it is first that you can, by using conformal transformation, you can always map this region into hemisphere by rescaling it. And if you have a hemisphere where pictorially it's half of the space, so suppose this is a space-like section of conformal field theory, it's a half of the space. Then there is a Rindler Hamiltonian, which is actually a boost Hamiltonian associated to this half of the space, which this is a fixed point. So this is exactly the conformal transformation which fixes the boundary. And so then you do the conformal transformation of this generator back into this region, and this gives you the modular Hamiltonian. So with this, therefore, what this is showing is that therefore this S of rho sigma in this case is given by, so suppose this is region A, then this gives you, this first term is minus of Ryu-Takayanagi formula, the Ryu-Takayanagi entropy. So this is the entanglement entropy, entanglement entropy for this for the state A, rho of A. So this is entropy for rho of A. And the second term is just an expectation value of minus of rho of sigma for rho. So namely that this is an expectation value of the modular Hamiltonian evaluated for rho. So this looks like a free energy. This looks like a free energy, right? The Hamiltonian minus an entropy. So this looks like a free energy. And in fact, this is actually a very useful analogy. So you can think of relative entropy as free energy for the modular Hamiltonian. Now, as I said, relative entropy is non-negative and vanishes when they coincide. So that means that by continuity, if you actually consider a small variation of rho around sigma, so suppose you consider infinitesimal variations like that, then relative entropy between them well, when del rho vanishes, it should vanish. But then actually del rho this vanishes if and only if del rho is 0. So that means that actually it should start quadratically in del rho by continuity because this is positive, non-negative, and vanishes if and only if del rho is 0. So it should be quadratic. It cannot be linear because if it is linear, then it should be negative on one side or the other. So it should be quadratic. So it should have some kind of quadratic expression plus some higher order, right? And in fact, in quantum information theory, this is known as quantum Fisher information. The Fisher information is sort of natural notion of metric in the space of probability distribution. And in the quantum version, this is a metric in the space of density matrices. So this is known as Fisher information. So this starts with a quadratic part. So that means that, of course, this is 0. This will be 0 in the linear order, in order del rho, right? And it was shown by various people. I have reference here, but I guess you have citing them, it gets complicated. That it was shown that if you take sigma to be pure ADS geometry, and if you consider rho to be infinitesimal fluctuation about that geometry, then this is actually equivalent to linearized Einstein equation. In that case. So namely, if you characterize rho, state rho as some fluctuation of the geometry around the pure ADS, this gives rise to actually constraint on the geometry that it has to subject to the Einstein equation. So it's very interesting that you can actually derive, in some sense, Einstein equation from this type of information theoretical consideration. Yes? Yeah. Yes. It's a non-local thing, but in this kind of linearized situation, it's reduced to a local equation because fluctuation at different points can be treated separately. Okay? And then subsequently, Nima Lashkeri and Jennifer Lin, Bogdan Stoika, and Mark van Rangstonk and myself, for example, have shown that we are interested in extending this to higher order in the fluctuation, and we show that we are able to show that actually, in general, the notion of positivity here is related to positivity of certain kind of energy associated to the entanglement wedge. But again, I only have like 10 minutes, so I am not able to go into that. But I do want to mention one more thing, which is sort of one of the main things that I wanted to convey, which is that this type of entanglement, entropy inequality and equality actually give you some conceptual reason of why this reconstruction of bulk works. So let me try to end this lecture by explaining the basic idea. So again, the idea comes from this, this relation. By the way, this is known as the first law of entanglement. In analogy with the first law of thermodynamics. Okay, so now let me actually try to explain why this is related to the entanglement wedge reconstruction concept. So, so first of all, again consider this situation where you have this region A, and then you have Ryu-Takayanagi surface associated to A, and then you have this bulk region, which I denote by small a. Okay? So, so if I compute, so suppose rho is some state in the Causal subspace, and then consider entanglement density matrix associated to that, and so it is computed by CFT Hilbert space restricted to the region A of rho A log of rho A. Okay? And this is given by 1/4g Newton times area of sigma A minus, and it was shown by Faulkner, Lukowitz, Maldacena. Faulkner, Lukowitz, Maldacena in 1307-2892 that the correction can be can be regarded as entanglement entropy calculated for the bulk quantum field theory. So the leading part, if you expand it in sort of Einstein gravity with small fluctuation by loop expansion, the leading term is a classical piece, which is given by this Ryu-Takayanagi formula. But then there are corrections. And they pointed out that the correction can be calculated by thinking that, well, you have, in the bulk, you have quantum field theory in the small fluctuation. So then you can divide the Hilbert space of that quantum field theory into region small a and its complement. And then you can consider entanglement density matrix for that quantum field theory and compute the entanglement entropy. This is actually order 1 as opposed to classical. This is order h bar, if you like. So order h bar correction can be calculated as entanglement entropy in the bulk. Okay? Now, but this is a classical piece, and then this is a quantum piece. And in some sense, you can think of this as the expectation value of some operator, because this is something that you can compute for given geometry. So you can imagine that there is actually an operator. Sorry? Both are UV, this is UV divergent and this is UV divergent. There is a order h bar UV divergence also possibly contained in here. So you can imagine that there is an operator in the quantum theory of gravity whose expectation value gives you, for rho A, gives you area of sigma A. because evaluating operator in semi-classical case is just evaluating the, so this can be calculated in terms of the metric in the bulk. So you can certainly consider that there is an operator whose expectation value gives you area. So that means that, okay, so for simplicity, let's also divide by 4g Newton. So that means that S of rho A can be evaluated as trace of A hat rho A plus S of rho A. So namely that left-hand side is given by boundary CFT density matrix, and the right-hand side is given by the bulk formula like that. So this is an operator in the bulk Hilbert space because you are evaluating it. So because in the bulk you have a geometry and fluctuation around it, and then small a because this is specifying the bulk quantum state for which you. Oh yeah. So I should have written like that. Yes, thank you very much. Yeah, this holds only for cold subspace. That's important. So now let's apply the first law of entanglement for this formula. So if I apply first law, what's going to happen? Well, first law states that 0 is equal to S of rho plus del rho. And let me see. Yes, but S is this quantity. S is this quantity. So that means that this is equal to trace of H of rho del rho minus del of S rho. Right? But now we know what rho, S is. S is this one. So that means that if I calculate del of S rho A, this is equal to trace of A hat del rho A plus trace of H of rho A del rho A. Because we can use this. So this inequality means that delta of S rho is given by trace of H rho delta rho. And this is true for any density matrix. So in particular, if I apply this over here you have S of rho A, but that, according to the first law of entanglement, should be given by trace of H rho del rho. Okay? On the other hand, this is equal, according to this formula, is equal to trace of HA delta rho A. So this is interesting because this means that you can actually compare this with this, and this should hold for any variation. So that means that operatorially, there must be a relation between this operator and this operator. So actually, I'm going into 0 minutes, but I guess I started a little bit late. Maybe 5 more minutes? Yeah. Okay. So I'll try to come to logical conclusion in 5 minutes. So this means that if I consider projection of modular Hamiltonian for the cold subspace, note that this is acting on the conformal Hilbert space. So if you consider projection of this to the cold subspace, then this is given by A hat plus the modular Hamiltonian for this region A. So there is such a relation that you can derive. Okay? So this is actually a very important relation because you can, now that you know the relation between modular Hamiltonian, you can plug that back into relative entropy and derive the following inequality. So this is algebraic. You can just do some algebra to prove it, and let me just state the final expression after going through the algebra. So if I use this relation, and so by remembering that the relative entropy is given by expectation value of modular Hamiltonian and entropy itself, you can derive the formula that relative entropy between entanglement density matrix on the boundary is given by relative entropy of the corresponding density matrix in the bulk. So what is this telling me? What this is telling me is the following. So suppose you have two states, rho and sigma. So both of these belongs to the code subspace. So these are both some state in the code subspace. And then you consider region A and region A. And then you consider Ryu-Takayanagi surface. And then you can consider domain A. What this is telling you is that if you consider density matrix rho of A and sigma of A, and rho of A and sigma of A in the bulk, then these two are the same if and only if these two are the same, and vice versa. So namely that whatever the change that occur over here, you can detect on the boundary. And similarly, whatever the change you make on the boundary, you can detect in the bulk. So that means that, for example, if you excite this thing infinitesimally by applying some local operator on this side, that can be detected by the boundary. So that means that you can actually simulate that effect by doing some operation on the boundary. This is actually the basic idea of reconstruction. And in fact, it was proven in the very nice paper by Shi Dong and Daniel Harrow and Alan Wall that this equality is equivalent. From this, you can prove that for any operator in code subspace, acting on the code subspace, there is some operator on the CFT side, such that for any state in the code subspace, you can reconstruct. So namely, that operator acting on this code subspace can be reconstructed by the operator acting on the boundary. So this gives you sort of a priori construction of why local excitation in the entanglement domain can be reconstructed from conformal field theory operator on the boundary. So this may be a good place to stop. So thank you very much for your attention.